Good afternoon. I am Monica Simeoni, and I am part of the Scientific Organizing Committee, and I work in the Clinical Pharmacology Modeling and Simulation Department at the GSK. Today, I'm delighted to chair this very interesting session on neurodegenerative diseases. Our first speaker is Al-Zahra Hamdan. Al-Zahra obtained her master's degree in pharmaceutical sciences from Uppsala University and is currently a first-year PhD student at the Pharmacometrics Research Group at Uppsala University. Her doctoral research is focusing on developing methods for assessing treatment effects in rare diseases. The title of our presentation is Item Response Theory Analysis of the Scale for the Assessment and Rating of Ataxia in Autosomal Recessive Cerebellar Ataxias. Al-Zahra, the floor is yours.
Thank you. Good afternoon. I'm here today to present the results from our work in which we have used the innovative methodology in pharmacometrics, the item response theory, to analyze data on the item level from clinical outcome assessments. And in this work, we have analyzed the scale for the assessment and rating of ataxia, which is used to evaluate the disease severity from cerebellar ataxias, and in this work specifically autosomal recessive cerebellar ataxias. So cerebellar ataxias, or ARCAs, is a heterogeneous group of rare and ultra-rare neurodegenerative diseases. Its main characteristic is lack of coordination. It affects the cerebellum and associated tracts. It's a progressive disease, so at the end of stage of the disease, the patient may completely lose the ability to move and ambulate. It's a genetically defined disease with more than 200 disease types. In many of those, the number of patients can go down to only one subject per disease. So far, there are many disease-modifying therapies on the horizon. However, there is a scarcity of robust trial designs in cerebellar ataxias and in rare diseases in general. So in this, you can see how the ataxia affects the patient's ability to keep the balance and to move. The most widely used outcome measure for ataxia is called SARA scale. It's a relatively new outcome assessment. It was developed in 2004. It's a clinician-reported outcome, so the clinician asks the patient to perform certain tasks and then rate the performance of the patient on certain grading scale. The SARA scale has 8 items measuring the gait, stance, sitting, and speech disturbances, in addition to some fine movements and rapid movements tests. So those on the right are measured twice on the left and right body sides, and then the mean of both is reported. The total sum score of SARA ranges between 0 and up to 40 in most severe ataxia. Now the question is, can we use SARA as a primary outcome measure in treatment trials? So far there is a big discussion about this in ataxia field, but there are some concerns raised by regulatory agencies and recent studies concerning the SARA metric properties. So they're discussing now doing some modifications to optimize the SARA. However, there is a scarcity of data evidence and validation of such modifications and for the SARA itself. So far, the analysis was done using the total score, ignoring the item contribution from each item. So in our work, we aim to evaluate the metric properties and performance of the SARA using item response theory. So here is a representation of the IRT model for SARA. So the different items from SARA reflects one common underlying variable, which is the ataxia severity. So in IRT, this ataxia severity is called latent variable. And in IRT, we quantify the relationship between the probability of obtaining certain score and the underlying latent variable for the subject. The most common way to quantify this relationship is two parameters, logit functions, which we have used in this work. And from this, we can have an idea about the characteristics of the scale, the item discrimination, and the difficulty of items. In addition, we can characterize the subject's characteristics, which is called the latent variable. Now, these item characteristic functions can be visualized using item characteristic curves, the ICC. We have the probability of obtaining certain score in the y-axis and the latent variable on the x-axis. In this figure here, you can see the ICCs for one item consisting of 4 response categories, ranging between 0 up to 3. And by looking at the ICCs, we can have an idea about the discrimination ability of the item by looking at the steepness of the curve around the midpoint. And we can have an idea about the difficulty of the item by looking at the latent variable at which the probability of a certain score is 50%. In our work, we have used data from the ARCA registry consisting of 1,932 visits from a total of 990 patients. Most of these patients have genetically defined diagnosis with a total of 115 genetic subpopulations. Here are the questions we want to answer from this IRT analysis. First of all, do all items share one common underlying latent variable? What are the characteristics and performance of the SARA assessment? And can we apply one IRT model for all genetic subpopulations? Starting with the first question, and in other words, in IRT words, we want to analyze the dimensionality of the assessment, if it's a unidimensional or multidimensional. And to do that, we have looked at the correlations between item pairs. First, we looked at the correlations in the original data set before applying any model, and then evaluate the correlations between residuals after model fitting. In addition, we have evaluated the average correlations for 100 simulations, and we did that for both the data and residuals. These 3 analyses were visualized in the upper matrices in these 2 plots here. In the lower matrix, we have did an additional evaluation, which is a VBC-like diagnostic, looking at the confidence interval for a simulated data set. Now, if we zoom into the first figure, and here is the data correlation between item pairs. And you can see that there are high correlations between all item pairs, which means that there is a common factor between these items, which is the severity of ataxia that we are trying to evaluate by this assessment. These high correlations were mimicked using simulations. And if we look at the VBC, we can see that the simulation described the data very well. So from this, we can apply unidimensional IRT model. Now, if we look at the residual correlations after fitting the model, we can see that there is only few correlations left, meaning that our model was able to account for these correlations we have seen in the original data set. And these, again, these correlations were mimicked using the simulations. And the VBCs here looks good. Now moving to the second question, now we want to evaluate the performance and the characteristics of each SARA item. And to do so, we have looked at the item parameters, at the item characteristic curves, and the item information. Starting with the ICCs, again, the probability on the y-axis and the ataxia severity on the x-axis. And we have the ICCs for each of the item. And in each item, the different curves are corresponding to the different response categories in this item. Now, as you can see, if we move to the right with the ataxia severity. If it increases, there is a higher probability for reporting higher scores, which is what we expect in this. Now, if we look at the shapes of the different curves, so for those lowest and the upper category, it's a sigmoidal curve with a high steepness around the midpoint. And we have clearly defined ICCs for the categories in the middle. So we can see from the ICCs that all items have high discrimination ability and that the response categories were properly designed. Now, to evaluate the performance furthermore, we looked at the Fisher information as a function of the latent variable for each of the item. And the shaded areas here are corresponding to the 95% of the population. And we can see that all items are informative, but with different importance level at different disease severity levels. So all of the items are contributing to the SARA score. Now, finally, we want to evaluate the different genetic subpopulations and if we can apply one IRT model for those. So we looked at the model fit for each subpopulation. So here are the different genetic diagnoses we looked at with 3 or more subjects. First of all, we started with fitting one IRT model using the whole ARCA data set. We extracted the individual objective function values and then randomly selected one observation per subject to avoid the bias in the calculations. And then we calculated the mean of individual OFEs for each subpopulation and for the entire ARCA population. And then we calculated the difference in means along with the confidence interval. These results are, we analyzed them on the x-axis. Now the 0 point means that there is no difference between the subpopulation comparing to the entire population. If we move to the right, then there is a worse fit than expected, and to the left there is a better fit than expected. Now if we look at the results, so from these different genetic diagnoses, the second one to the last one, all of the confidence intervals represented by the error bars here encompasses 0, so meaning there is no difference between the subpopulation and the entire population. On the opposite, if we look at the first group in the top, the permuted group, so this is a hypothetical subpopulation we created by permuting the subscores across individuals. And the purpose was to see how subpopulation with different item patterns would perform in this analysis. And the performance here agrees with what we expect. It fits worse than we expect. So there is an absence of evidence for differences between genetic subpopulations. Now to conclude, we have seen that SARA is a unidimensional assessment. It captures one single latent variable. SARA is a well-performing assessment with high discrimination ability. All items are informative with different importance levels, with different disease severity levels. And one IRT model is applicable across all genetic subpopulations, and meaning there is no item patterns differences between these subpopulations. And from this, we have shown evidence of the adequacy of the SARA using IRT analysis. And now we have an IRT framework that describes SARA on the item level and describes the disease severity of ataxia patients. Finally, I would like to thank our collaborators from the Evidence R&D Consortium, which was funded by the European Joint Program in Rare Diseases. Another aspect of this project is going to be presented by Niels in tomorrow's poster session. Thank you for your listening.
Thank you, Al-Zahra. And now we are open for a couple of questions. Maybe I start with one. Is there anybody? No, just a general question from me. Are there limitations in considering so many genetic subpopulations? I mean, which are the characteristics that you have to select?
So in general, with the IRT analysis, the one limitation is going to be the few number of individuals per each subpopulation. So we couldn't apply one IRT model for each subpopulation. So the workaround for this was to evaluate the model fitness when we use one model. Yeah.
Okay, thank you.
Hi, Laura from Leiden University. So I was wondering, because you get these scores, and often what they do is just take the sum of all the values, and did you consider seeing how this would compare to using your item response theory model?
So we didn't look at the total sum score, because the purpose from this was to look at the performance of each item. So,
okay. Yes, thank you.
Thanks.
So, hi, I'm Niels Hendricks from Hintam. So, in your introduction, you said that one of the goals of this project was to evaluate the score on the individual scale. And my question would be, have you considered trying to remove some of the items to see if you lose statistical power or predictive power?
So what we did is trying to remove some of the items and look at the total information, total Fisher information. And whenever we remove one of the items, we lose some information. So this is what we did. And another thing is that with Sarah, there is only 8 items, so it's very few and takes only 15 minutes to perform. So this would make it less important to evaluate if we can remove some of the items, especially that all of them are contributing very well to the Sarah assessment. Yeah.
Okay, thank you.
Thanks.
So, if there are any more questions, we move to the next presentation. Thank you very much.
Thank you.
For the very nice presentation. Our second speaker, closing the first day of the conference, is Alessio Paris. Dr. Paris is a senior modeling scientist at Fondazione de Microsoft Research, University of Trento, Centro for Computational and System Biology, COSBI, in Rovereto, Italy. He obtained his PhD degree in physics from the University of Padua. After that, he spent several years working in the field of material science before switching to system biology. He has been working on collaboration with the pharma industries, and his current activities include the QSP models of biomarker for neurodegenerative diseases and PBPK models of Fc fusion proteins. In addition, he has been also investigating methodological aspects of deterministic and stochastic simulations. Today, the title of his presentation is an age-dependent QSP model of neurofilament trafficking to optimize treatment in neurodegenerative diseases. Dr. Paris, the floor is yours.
Thank you for the introduction. Thank you to the organizers for the opportunity to present our work. And the model I present today is the fruit of a multi-collaboration of COSBI with Biogen, in particular with Ivan Nestorov's pharmacometrics team, and with people from the medical teams that provided the data from the clinical trials. And the goal of the collaboration was the development of a QSP model of neurofilament trafficking from the nervous system, from the neuron, to peripheral tissues, such as cerebrospinal fluid and blood. Neurofilament is a protein polymer, is one of the major structural components of neurons. And at all ages, even in physiological condition, a small fraction of neurofilament is released from neurons. It leaks to CSF and to blood, where it can be detected. And the important thing is that with aging and in the presence of some neurodegenerative diseases, the neurofilament levels are significantly increased with respect to the healthy condition. And this explains why neurofilament is considered in the last years as an important biomarker of neurodegeneration. Is used in an increasing number of clinical trials as an endpoint, and also for drug approval, such as in the case of tofersen, which is one of the drugs I discussed later. And there is also preliminary evaluation of the use as a prognostic biomarker. And the model development followed this biological indication. So we started from the adult healthy model. And you see the model diagram is quite simple because we have neurofilaments synthesized and degraded in the neurons of central nervous system, CNS, and peripheral nervous system, PNS. Some neurofilament is released, exit from the neurons, is transported to the surrounding environment, to CSF, where it circulates between the cranial and spinal part. It's transported to blood, where it's finally cleared in our model. The model was implemented as a set of ordinary differential equations. We did preliminary parameter estimation based on literature data, some sensitivity analysis, and we included also aging effects. I will spend a few words in the next slide. But this was the starting point for the development considering neurodegenerative diseases, and we started from the case of pediatric spinal muscular atrophy. And you see that the differences are very minimal with respect to the previous model diagrams. Fundamentally, we have an additional extra leakage from the lower motor neurons represented by the red arrow due to the disease. And of course, our main interest is the modeling of treatment. In particular, we focused on the antisense oligonucleotide nusinersen, which is commercialized as Spinraza. And we are leveraging on the results from this model part to predict in silico scenarios. The other step we consider is the adult SOD1 ALS, amyotrophic lateral sclerosis, so it's a familial subtype of ALS. And also in this case, you see that the model extension is minimal. In this case, we have two additional reactions because we have contribution both from the upper motor neurons, fundamentally from the cortical spinal tract, and from the lower motor neurons. And also in this case, we are interested mainly on the treatment. In this case, the drug is tofersen. There are also some features that are not visible from the diagram, and they are related with the age dependency of the model. In the case of the healthy adult condition, we included a phenomenological function modeled on CSF data of neurofilament in the light version of the neurofilament. This function was tested on an independent set of data in blood, and this function represents fundamentally the increased leakage from 20 to 90 years. On the pediatric side, so SMA, we had to include several features typical of the pediatric development of child development because we are following the patients for several years, so the volumes change, the nervous system develops. So we consider the volume growth, implementing it as a set of additional differential equations in the model, and these equations are modeled using real population data. And we also included, modified the neurofilament synthesis, trying to mimic the proliferation and pruning of the neurons that happens between birth and around 10 years. And if we look at treatment, which was the core part of our model development, the two drugs, nusinersen and tofersen, are targeting different diseases, so their action from a biological point of view is different. But if we look at the action on neurofilament, the result is that we have improved motor function, then decreased neuronal degradation, and a decreased neurofilament release to CSF and blood. So from a modeling point of view, we treated them in the same way in the two models. And since we don't have all this complexity, we resorted to transit compartment models, whose output function is an effective term affecting the extra leakage from the neurons, while the input is provided by two PK models of the two drugs, respectively. So we had the chance to integrate also this PK part. By the way, Michael Monini is here at Cosby, is here at Page, and he has a nice poster with an update of the tofersen PK model. And this also allowed us to simulate individual administration protocols, and this was particularly important in the case of SMA because the data came from several clinical trials with heterogeneous treatment. You can imagine administering to pediatric patients. But with the PK integration, we could simulate all the treatment protocols, and we divided the data following a training validation approach. So most of the data were used for training, fundamentally fitting the same time series in CSF and blood, and building parameter distributions derived from these fits. These parameter distributions were tested on several cohorts of patients reserved for this purpose. Fundamentally, we predicted the untreated and treated range and verified that the treated patients overlap with our treated predictions. We approached the problem in the same way for SOD1 ALS, so the training fundamentally was fitting the time series in CSF and blood. In this case, I reported also some quantitative measure of the fit accuracy. The normalized root mean square deviation, the median is around 25%, and it corresponds to the example reported here. In the validation, in this case, the untreated condition is trivial, so we are simply comparing the treated predicted bands, and the accuracy is assessed with a score going from 0 to 1, so 1 means perfect overlap with the data, and as you can see, this is true in most cases. One final application we consider for SOD1 ALS is about disease onset, because we had data from 6 patients followed from the pre-symptomatic to the symptomatic phase, so the plots on the left, and we introduced a logistic function that could fit the data in all cases and derived additional parameters for the model for these functions. And we combined the results from the treatment with the disease onset, and in this way we could fit the time series of several patients that started the treatment not with steady neurofilament levels, but probably still in the onset phase of the disease. And I think we think that this is very relevant because it opens the way to simulate scenarios at an early phase of the disease development, or even, as in this example, in the pre-symptomatic phase. All these results, if you are interested in additional details, are already published in the case of the healthy adult model and for SMA, while we have work in preparation with the results about ALS. And to go to the conclusions, this is a very concise summary of what we've done. So we developed this QSP model for the adult healthy condition that is meant to be the starting point for every development, and for two particular diseases for which we also had treatment data. But in our opinion, this, the model could work as a sort of general platform and could be in principle extended to other drugs or to other diseases in a very straightforward way. And we are currently using the results we obtain from the parameter estimation to investigate in silico scenarios with the aim of assist the clinical program development. In particular, we are developing scenarios ready for incoming data in the very near future, and also for trials that could start later. And one possible extensions of this work could also be to link neurofilament and to link the model to other parameters of disease severity, such as clinical scores. And finally, we are also evaluating the possibility of integrate the model with information from additional biomarkers. I can't disclose which biomarkers, but in any case, the idea is to improve the details of the model in the neuronal compartments. And that's all. Thank you for your attention.
I'll squeeze 3 questions in one. So first question is, how fast is the moving of the neurofilament from neural system to CSF and to blood? Second question, how you manage to get so many data from each patient? I know it's very difficult to have CSF sampling. And third, in my experience, the data very variable, but your plots looks like a very nice lines for each patient. So if you can comment on those questions, thank you.
Okay, regarding the first question, the transport to the CSF is very fast. I mean, in a few hours, and also to blood because it depends fundamentally on CSF recycling. How long it stays in blood, it also depends on which type of neurofilament we are looking at. So we discovered that light neurofilament is cleared faster, for example, than neurofilament heavy. The second question was about, the data abundances. Okay, and the reason is that in CSF, and the reason is that the drugs both drugs are administered intrathecally. And for example, for ALS, it's 4 weeks. So each 4 weeks, the patients receive the treatment and the spinal puncture, and so CSF data are collected. And regarding the smoothness of the curve, probably it's because the scale difference between the starting levels and the treated levels are very high in some patients. So probably I chose one of the best curve I could show.
Some other question? Just for me, so you said that you perform a sensitivity analysis, so regarding the compartments that are relevant for the diagnostic of the neurofilaments, which are the parameters that are more driving the yeah, sorry. No, I was just asking that, given that you said that you perform a sensitivity analysis, I was interested to know regarding the compartments that are relevant for the diagnostics of the neurofilaments, which are the parameters that are more sensitive?
Yeah, the relevant compartments in our model is CSF spinal and blood compartment. For CSF, fundamentally, the most important parameters is the leakage rate from neurons. And surprisingly, the sensitivity is low with respect to the turnover of CSF and also the transport to blood, but probably that's something related to how we develop and draw the model. In blood, of course, again, the leakage, because it's the source of neurofilament, and clearance.
Okay, thank you. Please.
So, just because of curiosity, you have an age-dependent component in the model. Suppose we can live 1,000 years. So, does it mean everybody, if he lives 1,000 years, will develop the neurodegeneration disease?
That's an interesting question because maybe it was not clear, but also in the healthy condition, the increase is mildly exponential. So we are losing more and more neurofilaments as we get older. And it was sort of exercise. We tried to compare, for example, the damage in ALS with a fictitious age in an healthy patient. It was just a play, so don't take my word as a true result. And the correspondence was that an ALS patient corresponds to a subject around 120 years. So from our results, it's suggesting that in any case, we are doomed to lose too many neurofilaments, to lose too many neurons.
Okay, thanks. And is there active mechanism to repair? I mean, as we know in current knowledge, is there some physiologically based thing that's happening in the brain for repair?
Okay, not in our model, not in the adult model. So I'm not an expert of neuronal biology, so I don't know how and if it could be included. As I mentioned, in the pediatric case, we are trying to mimic the neuronal system development. So in the first year, we have proliferation of neurons and then pruning. And we try to include it with a phenomenological function following data from dendrites and axon development.
Okay, okay, thanks.
If there are no other questions, yeah, I would close the session for today, and thank you to our presenters for the excellent presentations and for the and for your attention. And please remember that tomorrow morning the sessions starts at 8:30 with the Louis Scheiner student session. So be on time and see you tomorrow. Thank you.